All right, we're back. We're still on page 8 of notes 2 of Calc C, and we were talking about Taylor polynomials, and we're about to talk about, or do an example, I guess, of dealing with the Lagrange error bound. And so the real issue with Lagrange error bound, because it's pretty easy to remember, it's the absolute value of the error is less than or equal to m times the absolute value of x minus a is the center. So the absolute value of x minus a to the n plus 1 over n plus 1 factorial, right? The hard part is, what is m? And it's a weird question to answer. And so you'll find frequently, as I mentioned in the previous video, and is highlighted here, frequently m is just basically given to you. Like here, m is definitely 14. I don't even need to know what the problem is. That problem is definitely telling me that m is 14. Because I know the sixth, not only that, I know that this problem would have been about a 5th degree Taylor polynomial, because they're telling me about the 6th derivative, which is 1 more than 5, which means that you must have stopped at 5 and now you're using the 6 to find m. So let's see if we can do this problem. So use your calculator to find the 3rd degree Taylor polynomial for f of x equals e to the 3x centered at 0. Use the polynomial to approximate f of 0.25, then find a value for m. This question could use some work. All right, so we're going to try to find m 2 different ways, basically. But first, we're supposed to use our calculator to find the polynomial. So let's share this. And so this is basically what I'm going to do. I'm going to start a new document, though. All right, so I'm going to do Taylor polynomials. So that's menu, option 4, and it's like option C, I think, and then enter. So it's probably worth your while to memorize menu 4, C, enter. I don't know. And I want it for e to the 3x, so e to the 3x. I always type this, but it's easier for you to use the template, e to the x. On the left-hand column, it's like below the exponent, which is below equals, which is below control. So find it there. And then x is the variable. Now I need to say what degree I want. So I'm looking for 3rd degree. And then the center is optional if the center is 0. Like by default, it wants to start at 0, or be centered at 0, I should say. So I'm going to go with this. I'm going to define this as p of x. I was going to say f of x, but that doesn't make sense because f of x is supposed to be e to the 3x. So this is going to be this, and then I'm going to actually define that. F of x is e to the 3x. Okay, so one of the things we want to do, we want to approximate. So p of 0.25. This is approximately what I think e to the 0.75 is, because if I take 0.25 and I plug it into f of x, I get e to the 3 times 0.25, e to the 0.75. So that's my estimate of e to the 0.75. Now what I want to do is figure out how wrong might I be. So m is supposed to be the maximum of the absolute value of the n plus 1st derivative on the interval from the center, which is 0 in this case, to the value I'm approximating, which is 0.25. So 0 to 0.25, I need the maximum of the absolute value of the n plus 1st derivative. The question is, what is the n plus 1st derivative, right? So to get the 3rd degree polynomial, I needed to use 3 derivatives, the 0th, 1st, 2nd, 3rd. That's like, it's 3 derivatives in the original function, but use up to the 3rd derivative, let's say. So to find m, I need to look at the 4th derivative. So I need the 4th derivative of f of x. So I'm going to have the calculator find that for me, which is not like super hard to do, but you know, when the calculator is right here, why not use it? Okay, so I get 81 e to the 3x. Now I need the maximum of this on the interval from 0 to 0.25. So what I'm going to do is I'm going to do it on the graph page. So graph, I'm going to actually change, should I change the window? I don't know. So what am I graphing here? 81 e to the 3x. I only need it from 0 to 0.25. It's going to be really hard to find the y value. Well, not really hard, but harder than you might think to find the y value. So I'm going to look from like negative 0.05 maybe to 0.3, right? Because I'm only looking between 0 and 0.25. So I did 0 minus 0.05 and 0.25 plus 0.05. And then the y values, like I know that it's not negative. It's very positive. Basically, you're doing like 81 times a lot. Well, maybe not a lot. I don't know. Let's start with 81. Bigger than 81. So here's a little thing you can do. So I'm going to do this. That was not what I wanted to do. I'm going to change the window, menu 4, enter. I'm going to make the maximum just be f1 of 0.3. And the calculator is going to do the work and just like do it for you. So there you go. All right. So you can see this is an increasing function. So its maximum is at its right endpoint. In my experience, the maximum will basically always be at the left or the right endpoint. Just saying, like you can't really take that to the bank because there could be a critical point in the middle where somehow the n plus first derivative changes increasing, decreasing. I don't know. I've just never seen one like that. It could happen, I suppose. Like I could come up with a scenario, I think, where that happens. So I'm just going to trace to 0.25. So I'm using 171.477. So let me just write that down. M is 171.477. All right, I'm going to go back to, so let me just use it, right? So the error then, I should have stored that. Going back, not doing my best here. How am I going to store that? I'm going to put a point on. Oh, you know what it is? If you're tracing, let me try this again. Trace 0.25. If you press enter after that, it like pastes a point down there, and then you can escape, and it's there, right? And what's nice about that is that I can do, I can store it. So I press Control and Menu. It opens this, and then I choose option 5 to store. I'm going to store this as M, right? Because that's what it is. So let me go back here. So the maximum error is going to be M times the absolute value of X, which is 0.25, because that's where we're approximating, minus 0. Then to the n plus first. So we use 3 derivatives to get our polynomial. This is to the 4th. And then over 4 factorial. This should be the maximum error that I can get. All right, so now the question I want to answer is P of 0.25, so that's my approximation. If I subtract the error, I know that that should be less than the actual value. Is that less than or equal to f of 0.25? And then also less than or equal to P of 0.25, my approximation, plus my error, so plus this. And I get true, which is almost telling me that I'm definitely right. I mean, that's a very small interval. It'd be like a weird coincidence. But like you could get the error very wrong. And because the error is very wrong, your interval will just be huge. And then your approximation is definitely gonna, like the true value is definitely gonna fall in there. But let's assume we don't do that, right? Don't make huge errors. So let's go back. Let me explain more of what I did, just because I know this is a lot. And you might have to watch, you might honestly have to watch this more than once, because when we're in class, people tend to have a lot of questions about this. So here, M, this is the maximum of the 4th derivative, the absolute value, technically the absolute maximum of the absolute value. Let's do this. There's like a weird way they sometimes write this for the AP exam. So this is, it's the maximum on the interval from 0 to 0.25 of the absolute value of the 4th derivative. And then this was equal to M. So what did we do to find that? We find the 4th derivative. Now the 4th derivative, in this case, the 4th derivative is always positive, so we don't really need the absolute value when we're like doing the thing. But that's what we did. 2, we graphed the absolute value of the 4th derivative. And 3, we find, I guess, the maximum on 0 to 0.25. So that's what we did there. It's kind of a lot of work. And also it involved us using the calculator, and also the biggest crime involved here that we committed is that technically the M that we found, so this isn't going to work for a really clear reason when you think about it. In our case, M was equal to exactly 81 times e to the 0.75, but this is what we were trying to approximate, right? So why would I have just multiplied what I was trying to approximate by 81 and use it for error? Like, no, you can't do that really, because if we knew the error, then we would know automatically what the value of the actual function is. So this has a logical inconsistency, but it's still a good problem because it makes you think about it and do it. here's how you're actually going to do this, right? So the fourth derivative, so this is our actual way that we would do this by hand. The fourth derivative is 81 e to the what? Oh, 3x. Okay. So what we're trying to do is we're trying to find, we want to approximate or put a bound on the maximum on 0 to 0.25 of the absolute value of the fourth derivative, right? So that's our goal. That's what we're going to use for m, is our approximation of this. So you actually like don't really find m, you find like a bound for m and then use that, and m is already a bound for something else. But what I'm going to say is that e is definitely approximately 3. Now, if you're fancy, you just need to use something bigger than e. So e is like 2.718. So 2.72 would work. But what powers of 2.72 do you have memorized? I don't have a lot memorized. So I'm going to use 3 because it's the closest convenient thing. That's basically why. Right? So this, I know I'm going to be doing, I know that I should end up with this, e to the 0.75, right? So e is approximately 3. 0.75 is less than 1, but it's also approximately 1. So I'm going to use, so I'm going to say this is definitely less than 81 times 3 to the first power, which is 243. And so we estimated, and we're like, it's different, right? I'm using 243. This is the value the calculator got. It's different, but the key is it's bigger, right? So if I use this as my bound for m, then I'm going to be okay. So here, I'm going to say that I know f of, so the absolute value of the error is less than or equal, is definitely less than or equal to 243 times the absolute value of 0.25 minus 0 to the fourth, and then over 4 factorial. Definitely less than or equal to that, which means the true value, so let's call this capital E. The true value of the function, I know that p of 0.25 minus the error should be less than or equal to f of 0.25, which should be less than or equal to p of 0.25 plus the error. So that's it. Your goal is to be able to create this inequality. The decimal here has really kind of like bled in. Can I save that? Nope, cannot. Let me just put another decimal. There we go. So that's kind of your goal, is to be able to like set this up. Let's see how this compares. I mean, it's obviously going to work. Let's see how the error worked out though. I say it's obviously going to work because 243 is bigger, right? So my error would have been 243 times 0.25 to the fourth over 4 factorial. So this would have been my approximation of the error when I use the calculator's version of m, which we couldn't find anyway. But if we could find it, it was 0.0279. I'm using 0.0396, I guess. So they're really close. And the concessions that you have to make to get to the 243 that we used are worth it, right? I mean, it's less, much less effort. So that's what we're going to end up doing. So let me go back to the notes, one little thing, and then we're going to do a bunch of problems, which I think will help to clarify this. It's definitely like kind of a confusing thing when you first see it. Just keep in mind m is the weird thing. So the most common values that you'll be using for m for common functions, you typically use just 1 for sine and cosine. Like you can do better, right? Like if you know what you're approximating, maybe you know the thing you're approximating is less than, I don't know, you know, like sine increases from 0 to pi over 2. So like if you're approximating sine of 0.01, like maybe you could use 1/2 as m because it's bigger than what you need, but whatever. Don't overthink it, right? You get involved in overthinking, that's where trouble comes from. And then you'll pretty much use 3 when you're dealing with E. I mean, you can use other things, but then you have to know powers of those things, and that's kind of challenging. So I would say when I'm dealing with these, if there's a sine or a cosine involved in the m plus first derivative, I just say like, well, that's less than 1, and I go with it. And then if there's an E, I say, well, E is less than 3, so I'm gonna go with it. And then do my further approximations based on that. But Those are the things we use. So this is a good starter example, and we'll be back to do more in the next video. So I will hopefully see you there.